is a signal that spans 0 to T OFDM. Okay, where T OFDM is some time interval. Okay, we'll take one snapshot of this signal that we're going to transmit. So essentially, the signal starts with 0 and it ends with T OFDM and it ends here. And this is called in literature one OFDM symbol. It's called one OFDM symbol. Symbol is, notationally it implies this whole signal S of t. However, within one symbol, you're going to transmit many modulation alphabets. We'll come to that in a moment. Okay, you'll pack a number of modulation alphabets in one symbol. Okay, using this waveform that is being described here. Okay, so these called one OFDM symbol. I won't want you to confuse this symbol with typical modulation symbol that you encounter in single carrier transmission. We use this word symbol, in single carrier transmission, but this is a little different. This is a OFDM symbol, that is whatever is transmitted from 0 to T OFDM symbol. And what happens before and after? Well, it's in a continuous transmission, you will send one symbol after the other. Okay, you will continuously send one symbol after the other. So I didn't want to write the mathematical representation for the entire signal. It's sufficient to consider one snapshot of it because it's a block transmission. It's a block that spans 0 to T OFDM symbol. So what is that we are transmitting here? Well, this is S of t that is being transmitted in this duration. That is a summation of x of k, where x of k is the modulation alphabet. Okay, x of k is the modulation alphabet. What is the modulation alphabet? Well, we know BPSK, QPSK, MRAPSK, QAM, so on and so forth. Okay, so it could be either QAM or PAM or PSK, any one of those kinds. For each value of k taking value 0 to n minus 1, you have one modulation alphabet. If it is binary, this could take one of two possibilities, plus 1 or minus 1 with equal probability. Okay? Okay? So usually we choose the modulation alphabet such that it is a discrete sequence, and whatever is contained in the sequence, it is a discrete time sequence, and it's a random time sequence. It's a discrete random process, and we choose it such that this process, expected value of x of k equal to 0, usually we make the mean 0, and then the variance of this process x of k is equal to sigma x square, some suitably chosen constant, and xk are what I call IID random variables. You know what it means? IID random variables? Independent and identically distributed random variables. So expected value of xk and xm conjugate is equal to 0. That's right. No, they are IID random variables. This is a typical modulation sequence, right? That you have seen before. Okay, so our aim is to transmit n such modulation alphabets in a time interval 0 to T OFDM symbol. Okay, and how many bits each of modulation alphabet carries? That depends on the cardinality of the modulation alphabet, which is, it could be M array or Q array, whatever it is. So log m base 2 is the number of bits that each modulation alphabet carries. Okay, if it is M array, each modulation alphabet carries log m base 2 bits. Okay, and if you have n such modulation alphabet, it n times log m base 2 bits that you are going to transmit in 0 to T OFDM symbol. Okay. So now, as you very well know, if you want to transmit xk n points, xk are basically n points in some n-dimensional space. You need to transmit these xk's with a signature waveform, because you can't transmit xk's over the air, right? That's not possible, right? Xk's are discrete numbers, you can't transmit them. You need a waveform to carry that. You need a waveform to carry that. In traditional single carrier systems, you talk about rectangular waveform, things like raised cosine, MSK, things like that. I don't know if you have studied them, but xk has a waveform associated with it. Okay, so xk is multiplied with a particular waveform e to the power of j 2 pi delta f kt, and you can see that this waveform is a function of the index k. As k changes, the waveform changes, and you have to suitably choose this waveform so that at the receiver you can recover all the xk's without crosstalk from each other. That is, you are sending n complex sinusoids at the same time. You see, they are overlapping, but you have to be able to resolve them at the receiver and recover them without interference, mutual interference between them. Okay. That we will see in a moment how that can be accomplished. Okay, but we have not yet talked about the bandwidth of this system. That will come into the picture in a moment. Okay, we'll talk about the bandwidth of this system. That will come about in a moment. Okay, so we'll introduce some terminology. You can see that this waveform has some parameter called delta f. Okay, and this k times delta f, or rather delta f, is called the width of the subcarrier. Okay, we'll define what a subcarrier is. The width of the subcarrier. What is a subcarrier? Well, you can think of xk ranging from 0 to n minus 1, n tones being transmitted in frequency domain. You can visualize them as n tones being transmitted. This is a symbolic representation, this is not strict. x0, x1, x2 up till x n minus 1, each tone separated by delta f hertz in this is a frequency axis. Okay, this is not a strict frequency domain representation. We will see that, but this is a symbolic way of representing the system. Okay, then you might ask, what is the minimum delta f that is needed to ensure that these signature waveforms are orthogonal to each other so that we can receive them without crosstalk? Okay, when we build the receiver, we can figure out what is the minimum delta f needed. Okay, you can't choose delta f arbitrarily. You should follow certain rules. Okay, and if you have n subcarriers, the bandwidth of the system is, in a rough sense, k times n times delta f. But of course, you have to be a little careful about talking about the bandwidth. Am I visible in the video? Huh? What is that guy doing? Can you please make sure I'm visible? Okay? Yeah. No, the board is visible, but okay. When I speak, I think just please make sure I'm visible. You'll have to go back and forth. Yeah, we're talking about the bandwidth. Okay? In single carrier systems, I don't know if you remember, you have a signal x of k, p of t minus kt summation over, right? K. Remember? Where p of t is the pulse shaping filter. The bandwidth of the system in a single carrier system is dictated by the choice of the pulse p of t. Okay? And if p of t is rectangular, the frequency domain spectrum grows like sync in frequency domain. If the pulse is sync in time domain with certain width, it is a brick wall rectangular pulse in frequency domain. Okay, so there is a discussion of Nyquist criteria for zero SI criteria, Nyquist criteria for zero SI, and also the minimum bandwidth required transmit at a certain data rate. These are certain things you learn in this single carrier systems. Whereas this is a multi-carrier system. Why we call it multi-carrier? Well, what are the carriers here? The carriers are these k times, these are the carriers. The complex sinusoids are the carriers. Unfortunately, the spectrum of this complex sinusoid is not a delta function, is it? No. Why is that? It is limited to 0 to t OFDM symbol. Okay? These are not, you know that if you have a complex sinusoid, its spectrum is a unit impulse function at some point in frequency domain, right? But that is for a sinusoid that grows infinitely long. Okay, that is infinitely, the span is infinite in length. Whereas here, the sinusoid starts at 0 and it ends right here. And if you take the spectrum of a sinusoid, which is time limited, what would you get? Just roughly speaking, it is a sinusoid multiplied with a rectangular time window, and in frequency domain, it is a sync function convolved with some, right? So essentially, in frequency domain, to send one complex sinusoid between 0 to t OFDM symbol, you will have something like this, right? Isn't it so? You will occupy much more bandwidth than this single line that is shown here. That's why I said it is symbolic representation. Okay? So, the transmitted signal is limited in time, and therefore it is not limited in frequency. That is, the spectra is, well, it has infinite span. Okay? Well, there's nothing much you can do about it, except when you construct a signal at the edges of the band, you don't transmit some tones. Let us say your bandwidth is 20 megahertz. You don't fully occupy 20 megahertz. If you do, then there will be side lobes. That means you are exceeding the 20 megahertz assigned to you. So you reserve some 2 megahertz, and at the edges you null out some carriers. What do you mean by nulling out? Well, make some of the xk 0 at the edges. Okay? You make some of the xk 0. That is the beauty of multi-carrier system or OFDM, because there is a lot of flexibility in choosing how you transmit, because you can simply null out some tones and you can control the bandwidth occupancy. Okay? And in fact, you can control the bandwidth in a very flexible manner. Of course, it doesn't come for free. When you null out some tones, you reduce the bandwidth, but you also lose the data rate because you're not transmitting those symbols. Okay? You can't change the basic trade-off between data rate and occupied bandwidth. Okay? So, if I ask you to calculate the spectrum of S of t, how would you calculate it? Any idea? What is spectrum, or rather, spectrum is a loose word. If I ask you to calculate the average power spectral density of S of t, how would you go about calculating that? What is that? Yeah, so you're talking about taking a Fourier transform of S of t and squaring it and plotting it as a function of frequency. Well, that won't give you the entire spectrum. The reason is that there is still randomness in S of t because xk's are present. So you have to take the expected value of the Fourier transform squared of S of t. So how do I write it? Fourier transform of S of t that is S of f, right? And divided by, well, this is just energy, it's just a Fourier transform. What I would do is that I will take the expected value so that the randomness inside, it is still one snapshot, right? So what you would do is I will take the Fourier transform of this one OFDM symbol, I will square it, and I will take the adjacent OFDM symbol, I will take the Fourier transform, I will square it, and many such snapshot, I will average them and divide it by the total time taken, whatever this time is. Okay, so essentially I will take an S of t which is t seconds long, or t total seconds long. I will take a Fourier transform, and then I have to take the expectation, that is an ensemble average, but in real life you will take time average and calculate the average power spectral density. But of course, if it is a deterministic signal, all you have to do is take S of t, take the Fourier transform, you will get the spectrum of signal. But for a random process, that wouldn't work. So an alternative way of calculating the spectrum is take S of t, calculate its autocorrelation function, and take the Fourier transform of the autocorrelation function. That directly gives you the average power spectral density. Okay. So another way of doing it is calculate R of tau, that is S expected value of S of t, S conjugate t plus tau, that is R of tau, and the power spectral density S of f is equal to Fourier transform of R of tau. I don't know if this is visible on the. It is, okay. Have you done this before in random process course? Huh? Communications, yes. This is very important. When you deal with random signals, if you want to calculate the spectra of a random signal, you take the autocorrelation function, and then you take the Fourier transform of it. You'll get it. This is one way of doing this, and you'll get the same result by calculate. You can calculate spectra in another way by taking slices of the signal, take the Fourier transform, square them, and then average many such slices and divide by the total time taken. You will get the average power spectral density. That's what, if you notice, I am saying what is called average power spectral density. It's not just power spectrum. It is the average power spectrum, because if you just take the Fourier transform, there is still randomness in it, and you have to average over all the random variables involved. Okay, anyway, so the point here is an OFDM signal also has a power spectrum associated with it, and if you work out the math or if you simulate it, you will see that because the OFDM symbol is time limited, there will be side lobes at the edge of the spectrum. Okay, that's something you have to be aware of it. So if you drop some tones so that the side lobes reduce in intensity, that means you are sacrificing in data rate. Okay? There is some penalty to be paid. So efficiency of the system reduces a little bit. Okay. And you should also notice that we are limiting our discussion to a low pass or baseband signal, right? S of t is a low pass signal representation. It's not a band pass signal, but if you read Provocus, it nicely deals with representation of band pass signals and band pass systems. It conveniently represents. We can always represent a signal as a low pass equivalent signal. We don't have to carrier translate and work out. Okay, we don't need to do that because all that is taken care. If you read Provocus, you will see that. Okay. So the entire discussion will limit ourselves to low pass equivalent signals. Okay, which I call sometimes baseband signals. Okay. So you don't get confused when I say baseband or low pass. Okay. So what we'll now do is we sort of describe an OFDM signal, what it looks like. Now we'll receive this. Of course, I will not impose any propagation channel in between. That unnecessarily complicates the discussion at this point. However, we'll introduce additive white Gaussian noise, which is always present in the receiver, okay, which we cannot ignore, and develop a receiver which allows us to demodulate the information carrying symbols x of t. Okay. So I'm going to erase this. Okay, just because we don't have enough space. Okay, we'll keep that, the transmitted signal S of t. So what we're going to receive here is R of t, which is the sum of S of t plus N of t. Of course, again, this is a complete baseband representation where the noise N of t is also represented in baseband form. And you must recognize that this is the received signal at the front end portion of a receiver, which does not involve any type of filtering as yet. Okay, so this could be additive white Gaussian noise, which is not basically unfiltered noise. Do you know the difference between filtered additive Gaussian noise and unfiltered? Well, if you don't filter, when additive white Gaussian noise has spectra everywhere, right? It is flat in the entire frequency band. Of course, this is for a theoretical discussion. Okay, and if you filter the additive white Gaussian noise, well, it gets limited to certain band, and the power spectra is determined by the shape of the filter. Okay, so N of t again here is complex valued additive white Gaussian noise. That means N of t has a real part and an imaginary part. And Ni of t and Nq of t are statistically independent of each other. Okay, both are low pass signals, and the power spectrum of Ni of t and Nq of t are also similar with half power. If N of t has a density of N naught, Ni and Nq has a density of N naught by 2 respectively. Okay, so I'm going to write, just for the sake of completeness, I'll write it as expected value of N of t is 0. This is 0 mean, and expected value of N of t multiplied by N conjugate t plus tau is equal to N naught delta of tau. Is that right? Where N naught is equal to K times V, well, K times T, where K is the Boltzmann constant and T is the temperature in Kelvin. You know that, right? This is the Boltzmann constant. Of course, there is no bandwidth here because we have not filtered this signal as yet. Okay, this is the, I don't know if I spell this right, and T is the temperature in Kelvin. Okay, you can spend several hours discussing about thermal noise and how to model it, but we're not going to get into it. You can read Provaki's some other book, and it is additive. It is white because the power spectra of this is autocorrelation of N of t, R of Rn of tau, and what is the power spectrum of the noise here? Sn of f is, it is flat with density N naught, right? Why is it flat? It is, the autocorrelation is a unit impulse function with weight N naught. Additive, white implies all frequency contents are going through same attenuation. That's what is meant by white. Or if the shape is something else, we don't call it white, it is called colored. If it goes through a filter, the shape is determined by the filter transfer function, it is called colored. Additive white. Gaussian noise. What is Gaussian here? Well, N of t and I of t and Nq of t, the samples of these Ni of t and Nq of t are jointly Gaussian, and all these samples of Ni of t and Nq of t at different sampled at different intervals are statistically independent and zero mean, and each sample has a variance of n. Okay? That completely describes the additive at Gaussian noise. Okay? What is Gaussian here? The probability density function of this random variable n of t sampled at any given t as a Gaussian PDF. Okay? And if you take any other sample at a different t, they are statistically independent of each other, and both are Gaussian. So you can characterize, you can come up with a multivariate distribution function for that case. Okay? Don't mix up or confuse between white and Gaussian. White and Gaussian are different. They imply different things. White talks about the spectral content. Gaussianity talks about the probability density function of this random variable n. Okay? They're different concepts. Okay, so that's enough about modeling the noise. Now we need to develop a receiver in the presence of noise, and this should be what is called an optimal receiver. Okay, how do you define optimality? Well, there are many criteria. Some people say when you develop a receiver and when you measure the bit error rate, and the bit error rate should be minimum. So you define optimality with respect to minimizing the bit error rate. Or sometimes minimizing the bit error rate directly corresponds to maximizing the signal to noise ratio at some point in the receiver. Okay, maximizing signal to noise ratio at some point in the receiver. So we'll take the latter approach where we'll maximize the signal to noise ratio. We won't explicitly show that it is going to maximize signal to noise ratio, but you will sort of see it through in the various steps involved. Okay? Okay. So let's build the receiver. So S of t can be written as sigma xk phi of k t phi k of t. Okay, what is phi k of t? Well, this is phi k of t. The reason why I write it in this particular form is that it resembles something that you have seen. What is that? There are endpoints carried by some basis function. You did Gram-Schmidt, right? In digital communications, you did Gram-Schmidt decomposition. Did you do that? You have not. Mathematics you have done. Okay. Well, it's not a very complicated concept. If these functions f phi of k are chosen to be orthogonal, then given this, you can recover x of k from each x of k from s of t. So as long as phi k multiplied by, let's call it phi L and m of t, I'll put a conjugate here, integrate over 0 to t OFDM, because these basis functions are limited in time. This is equal to 0 for L not equal to m, and for L equal to m, this becomes a constant, well, some value. If we have this property, you can quickly show that you can recover x of k. X of k is s of t phi k star of t integral 0 to t OFDM. Well, actually, people write it as minus infinity to plus infinity because you don't have to limit this to some time. But anyway, let's say the maximum t OFDM is the maximum interval over which they are different. Okay. Well, how do you get this? You can recover x of k uniquely. Why is that? Well, you substitute s of t here, and you'll see that instead of k, I'll call it some m, just to make it a bit more convenient. This is equal to 0 to t OFDM. S of t is summation xk Pk of t, k equal to 0 to n minus 1, this whole thing multiplied by phi m conjugate of t dt. Now you can see that for k equal to m, you will get back xk with some constant and 0 elsewhere because the waveforms are orthogonal. Of course, you can always normalize them so that this goes to unity. Okay, you can always normalize these waveforms such that it goes to unity. Well, the Fourier basis functions do follow this property, right? You can think of it as a Fourier transform or inverse Fourier transform. Then the basis functions are complex sinusoid. And not only Fourier basis functions, there are many other types of basis functions that follow this property. Okay? I'll erase this. We'll develop anyway our receiver now in a moment. So, the question here is, these basis functions, you have to choose them such that they are orthogonal. That is, one multiplied with the other integrated goes to 0 with the different, if they are different waveforms. Okay. Okay. So we're going to develop our OFDM receiver now. Okay. So let z of m, it is just a variable, is equal to the received signal r of t multiplied with e to the power of minus j 2 pi delta f m t dt and integrated over 0 to t OFDM because our signals are time limited. Okay? So, well, let's substitute what r of t is and then we'll go through the steps and we'll see what happens. Okay? R of t is the signal S of t plus noise N of t. Of course, this whole thing is again low pass baseband. Okay? Carrier up conversion, down conversion, down conversion have been carried out. And sometimes this N of t need not be, totally flat. You could have a front end band pass filter with a very wide bandwidth, but that's okay. That doesn't change anything as long as you have a spectrum that is flat. Okay, that's good enough. Okay, we'll come to those things later, but we'll keep the system very highly idealized for the time being. Okay. So R of t is S of t plus N of t, and S of t is whatever the transmitted signal. We'll write it. Okay, 0 to t OFDM, and summation xk. Okay, e to the power of j 2 pi delta f kt, k ranging from 0 to n minus 1. This is our S of t plus N of t and the whole thing multiplied with the complex exponential e to the power of minus j 2 pi f delta f mt. dt. Okay? We'll bring the complex exponential inside and make certain manipulations. Okay? We'll take this integral inside, summation out, summation k equal to 0 to n minus 1 okay, and we'll take this integral inside, x of k will keep it here, integral 0 to t OFDM. If you can always drop OFDM and call it t, but Now this T is sometimes used in different systems, it means something else. So I just to make it different, I give T OFDM, okay? And e to the power of j 2 pi delta f k minus m multiplied by t dt. Okay, does it make sense? Plus integral 0 to t OFDM n of t e to the power of minus j 2 pi delta f mt dt. Of course, noise is also going to be processed in this particular manner. Okay, please tell me what is the minimum spacing delta f that is required to force the crosstalk between different carriers 0. Well, when k equal to m, obviously I get xm into t OFDM, right? This goes away, right? The integral. So what would we get? So let me write it here on this side. Okay, let me rewrite it. Z of m, which is our decision variable. By the way, what is the range for the m here? We are interested in 0 to n minus 1. So we want to recover all the n data tones, and Gm sort of contains x of m with some corrupting noise. Z of m is equal to x of m for k equal to m, and t OFDM is the integral, right? You carry out the integration, plus when k not equal to m, we have to see what happens to the rest of the integrals. Okay? Summation k equal to 0 to n minus 1, k not equal to m, we have to pose that additional constraint. X of k integral 0 to t OFDM e to the power of j 2 pi delta f k minus m into t, plus we have some noise, we will call it W of m. That is this noise. Okay, whatever that filtered noise is. Well, this is the unwanted term, right? There is a useful part, and this is the sort of interference coming from other. So you want to drive it to 0. So for a given choice of delta f, hopefully we can drive it to 0. So what would be the suitable choice for delta f here? Any idea? Well, let's think of delta f is equal to some q times q divided by t OFDM. Okay? Let's say q equal to 1 for the time being. So if I substitute delta f equal to 1 divided by t OFDM, and that would be a complex sinusoid integrated over a full period or multiple periods, depending on what this is, and that drives to 0. It's a complex sinusoid integrated. This goes to 0 if delta f equal to q divided by t OFDM. And what would be the minimum spacing required in this case between adjacent tones? Choose q equal to 1. So therefore delta f equal to 1 over t OFDM is the minimum spacing required between adjacent subcarriers to ensure orthogonality at the receiver. So therefore we end up with XM T OFDM plus WM for M equal to 0 to n minus 1. Well, you do have to talk about the noise WFM, what are the characteristics of this noise, because it did go through some sort of filtering process. Okay? So we can show that expected value of WFM is equal to 0. Why is that? Well, this is WFM. WFM, if you take the expectation, you move the expectation inside, and expectation is taken with respect to the random variable n of t, and that is 0 because everything else is a deterministic quantity. Okay? You know, we don't have a lot of time because if you have to go through every step, it will consume a lot of time. So I would skip some steps. I think they are good exercises for you, and this is one of those things. You can show that additionally, the expected value of W of m multiplied by W conjugate of n, where m and n are different integers, is equal to delta mn n naught multiplied by t OFDM. So what does it mean? For m equal to n, then we have expected value of W of m whole square, which is the variance of this new noise, and that would be equal to n naught times t OFDM that is the variance of W of m square. Okay? Why is that we need that? Well, unless you know the variance of W of m, you can't define the signal to noise ratio at the output of your receiver, which is of prime interest to us because we want to maximize the signal to noise ratio. Okay? Now, what is the signal to noise ratio associated with this decision variable z of m for a given m, for any given m? We can calculate it right away. What would be the signal to noise ratio? You know how to calculate it from here? We know the signal and we know the noise, and we want to calculate signal power divided by the noise power. And what would be the signal power? So, the signal to noise ratio for any given subcarrier SNR of m is the total signal power for that subcarrier divided by the noise power contained in the subcarrier. And how do you define the signal power? Well, x of m is a random variable. How do you define the power of a random variable? Any idea? Variance of that random variable, that is, so the variance of that random variable would be t square OFDM multiplied by expected value of x of m whole square, that is, the variance of the modulation symbols, divided by again the variance of the noise, that is expected value of W of m square. That would be equal to t square OFDM into sigma x square divided by what is the variance of W of m? Well, that is n naught times t OFDM. So 1t goes away and we get sigma x square divided by n naught into 1 over t OFDM. And what is 1 over t OFDM? It is very special, a special significance. 1 over t OFDM. T OFDM is the transmission time, and that is 1 over t OFDM is equal to delta f, the subcarrier spacing. So that is equal to sigma x square divided by m naught multiplied by delta f. Well, this really makes sense. The signal to noise ratio contained in one subcarrier is equal to the signal power, that is sigma x square, that is variance, you can make it unity if you wish, divided by the noise power contained in one subcarrier. And we do know that one subcarrier kind of occupies, although it occupies a lot of bandwidth, delta f is the minimum spacing required. So therefore n naught multiplied by delta f is the power contained in the filtered noise process. N naught is the power spectral density and delta f is the bandwidth associated with this complex exponential filter. Right? So it makes sense. This is the signal to noise ratio for m subcarrier, and you can see that it is not a function of m. So therefore all subcarriers do have the same signal to noise ratio. Of course, here the channel is unity. Channel is not changing between subcarrier to subcarrier. Okay? Well, that is the signal to noise ratio. Well, you may ask, is it the maximum possible signal to noise ratio? I'm not going to prove it, but you might have seen this orthonormal representation in many places, and it can be shown that indeed this is the maximum signal to noise ratio that you can ever achieve. And there is no, in other words, there is no other receiver that can give you a higher signal to noise ratio than this quantity. So maybe the other receiver, but it will still give you the same signal to noise ratio. Okay? We'll end this lecture by making one more remark about what is the transmitted signal power. It's not sufficient to talk about signal to noise ratio at the receiver. You also have to talk about what is the power that is incurred in the transmission, because we are transmitting n tones. Okay? And that can be calculated by calculating the energy of the transmission, E, that is equal to integral S of t square dt, and S of t being a random signal, you have to talk about average signal energy. Therefore, you have to keep an expectation here, okay, where the expectation averages over all the random variables involved, which in this case is xk. And again, this I leave it out as an exercise, little exercise for you, and you can show this to be this quantity n times t OFDM into sigma x square. Okay, I'm not going to derive all the steps. You can work it out yourself. So what happened here? The transmit power Pt, that is equal to E divided by total time taken, which is one OFDM symbol, T OFDM symbol, that is equal to n times sigma x square. And we know that each subcarrier has a power of, notionally, sigma x square, and noise power is m naught delta f. Here each subcarrier has a power sigma x square, and n subcarrier will have n times sigma x square transmit power. So increase n, power increases. Okay? Of course, bandwidth also increases, right? The total bandwidth, what is the total bandwidth, by the way? N times delta f, but that is not a strict definition because side lobes are still there. So you may have to null out some tones. Total bandwidth for this system is n times delta f. That is the total bandwidth of the transmission. Of course, I can multiply this by n, and call this the total transmit power, and n times n naught delta f is the total received noise power in a wider bandwidth. Right? That also makes sense. So I can write this as n times sigma x square divided by n times m naught times delta f, and that would be total transmit power divided by total noise captured in a bandwidth of n times delta f. Okay. How much time did we take today? 1 hour. Okay. Huh? I see. So you want to stop here? I think probably it's not a good idea to cram your heads with a lot of material. So you do go through this. Okay. because after next lecture you probably have to start implementing this. But you will not do a continuous time implementation. It would be a discrete time implementation, which I'll talk about in the next lecture. And you can use FFTs and implement this in MATLAB with 4 lines of code. This is not too difficult. Okay, we'll stop here. Yeah. Thank you.